Hello everyone, my name is Kirti. Today I am starting a new topic of new subject partial differential equation, MSc Mathematics Unit 1, Semester 4th. Partial differential equation. What does it say? A partial differential equation is an equation involving an unknown function of two or more variables and certain of its partial derivative. क्या कह रहा है कि पार्शियल डिफरेंशियल इक्वेशन कौन सी होती है जिसमें दो या दो से ज़्यादा अननोन फंक्शंस के वेरिएबल जो हैं इन्वॉल्व होते हैं और उनका पार्शियल डेरिवेटिव भी होता है मीन्स अ पार्शियल डिफरेंशियल इक्वेशन इज एन इक्वेशन इन्वॉल्विंग अननोन फंक्शन ऑफ टू or more variables and certain of its partial derivative. The kth order partial differential equation look like f d raised to the power k ux d k minus 1 ux dux ux up to x is equals to the 0. This is the kth order partial differential equation look like. Now, classification of partial differential equation. Differential equation is of two types. Either it is linear or non-linear. Now first is linear partial differential equation. The partial differential equation f dk ux dk minus ux dux ux x is equals to 0, which is the general kth order partial differential equation, is called a linear if it has the form summation alpha less than equals to k a alpha x d alpha u, which is equals to f of x. For given functions a alpha and f, this linear partial differential equation is homogeneous if f is equivalent to the 0, then it is called the homogeneous. When right hand side of the linear partial differential equation is equals to 0, then it is called the homogeneous linear partial differential equation. Now on the other hand, there is non-linear partial differential equation which is categorized into three parts, in which first is semi-linear partial differential equation. The partial differential equation 1 is called semi-linear. One is this fk dux dk minus 1 ux dux ux and x. Equation number 1 हमने इसको पॉइंट कर दिया है. और the partial differential equation 1 is called as semi-linear if it has the form summation alpha is equals to k a alpha x derivative of u d alpha u plus a naught dk minus 1 u du up to so on u x, which is equals to 0. Here highest order term is linear while other may or may not be. Here the highest order term is linear, other may or may not be. That means other may be of higher order or maybe of lower order. Now second non-linear partial differential equation is quasi-linear partial differential equation. The partial differential equation 1 is called a quasi-linear if it has the form a alpha dk minus u du u x bracket d alpha u plus a naught dk minus 1 u du u x is equals to 0. Summation over the alpha is equals to k. Here the highest order term doesn't involve the kth partial derivative as factor. Kth partial derivative as a factor involve नहीं करती. Now the third non-linear partial differential equation is fully non-linear partial differential equation. The partial differential equation 1 is fully non-linear if it is depends non-linearly upon the highest order derivatives, that is degree of partial differential equation is 2. Fully non-linear partial differential equation depend non-linearly upon highest order terms. That means when the degree of partial differential equation is greater than equals to 2, then it is said to be fully non-linear partial differential equation. Till here we have discussed the definition of partial differential equation, kth order partial differential equation. Now classification of the partial differential equation, that is linear partial differential equation, and second is non-linear partial differential equation. Non-linear partial differential equation can be categorized into three more forms, that is semi-linear partial differential equation, quasi-linear partial differential equation, and third is fully non-linear partial differential equation. So I hope till here you will understand what the all the things which I told you. Now the example of linear partial differential equation. The most commonly famous simple linear example of partial differential equation, which is also a linear, is that linear transport equation. Linear transport equation is the most simple partial differential equation with the constant coefficients. The basic form of the linear transport equation is ut plus summation I running from 1 to n bi uxi is equals to 0, where ut as it is and b is a vector of n components b1 b2 up to so on bn, and uxi is similar as ux1 ux2 up to so un, where b1 b2 up to so on is a b vector, and ux1 ux2 up to so on uxn is denoted by du is equals to 0, where b is a fixed vector belongs to R Euclidean space and Euclidean space. Now the transport equation is the simple partial differential equation with the constant coefficient. So the very first theorem in this partial differential equation is initial value problem. What does it say? Find the solution of the homogeneous linear initial value problem where transport equation हमें क्या दे रखे ut plus bdu is equals to 0 in Rn cross 0 to infinity, and initial condition दे रखे u is equals to z on Rn cross t is equals to 0, where b is a vector from Rn and g be a function from Rn to R, which is a non-function. Previous we have discussed the transport equation, where we know that's why we know that this is the general form of transport equation, which is a example of simple linear partial differential equation also. So let us discuss it. The proof of the initial value problem. Let x comma t be any point in Rn cross 0 to infinity. We have suppose any point x at time t, and let u be the solution of the given partial differential equation 1, which we marked here. Xt be any point in Rn cross 0 to infinity, and u be the solution of the given partial differential equation. अभी तक हमने क्या किया, u कोई भी सॉल्यूशन लिया इक्वेशन में फर्स्ट का, और एक्स टी कोई भी पॉइंट ले लिया था. अब हम डिफाइन करते हैं z इज इक्वल्स टू r से r में कोई भी मैपिंग है फंक्शन z, डिफाइन कर रहे हैं z ऑफ s इज इक्वल्स टू x प्लस एस बी एंड t प्लस s, डिफरेंशिएटिंग बोथ साइड विथ रिस्पेक्ट टू s, वट वी गेट z डॉट s. इसको हम z डॉट s से डिनोट कर सकते हैं ऑन डिफरेंशिएटिंग, और आइदर बाय डी जेड बाय डी एस. ठीक है, डी यू इज इक्वल्स टू एक्स प्लस एस बी टी प्लस एस. वी डिफरेंशिएट विद रिस्पेक्ट टू एस, सो हेयर इट इज द कॉन्स्टेंट एस की वैल्यू 1 ऑन बी प्लस यू टी एक्स प्लस एस बी टी प्लस एस. Okay, so z dot s is equals to 0 because u is a solution of 1. Here is the simple differentiating, so I hope you will understand it. Okay, if you not understand it, then please comment me and let me know in the description box, and I will let you know that how to solve this differentiation with respect to s. Now z is a constant function of s. Z is a constant function of s. यहाँ z dot s is equals to 0 हुआ था because u is a solution of partial differential equation 1. We suppose it before. Z is constant function of s. U is constant on the line passing through point x comma t in the direction b comma 1. हमने u कोई भी solution लिया था और that is passing on the line through any point which we suppose before x comma t in the direction b comma 1. Now u represented parametrically. U can be represented parametrically by x comma t plus s b comma 1 for all s belongs to R. Where this equation comes from? this equation is comes from the x plus sb comma t plus s. What we do here, x and t, x comma t plus s as it is, and b comma 1. So this is how you represent parametrically by this. Okay, so the line hits the plane हमने, let us suppose this plane is gamma, rn cross t is equals to 0 when t plus s is equals to 0, because here t is equals to 0. So x so in the above we let zs is equals to x plus sb is and t plus s. Let's say it is x and it is t. We are supposing in the plane gamma where rn cross t is equals to 0. So here t plus s is equals to 0, which is equals to s is equals to minus t at point x minus tb comma 0, because t is equals to 0 here and x replace into x minus tb. Since u is constant on the line and u x minus tb 0 is equals to g of x tb, by the initial condition we have taken in the statement that u is equals to g on rn cross t is equals to 0. Therefore u of x comma t, where t is equals to 0, is equals to g of x plus tb. We point it as equation number 2. Okay, so this is the solution of homogeneous initial value problem. This is the solution of the homogeneous initial value problem. Till here we have proved the first part, that if we have the equation ut plus bdu is equals to 0 in rn cross 0 to infinity, and u is equals to g on rn cross t is equals to 0, then we have the linear homogeneous solution, that is u of x comma t is equals to g of x minus tb. Now here is the converse part also. Conversely, it is to check directly, it is very easy to check directly that if g is a continuous, c dash means c means continuous class, g is a function which is continuous, then u defined by the equation number 2 we have discussed above is indeed a solution of 1. It is very easy. What does it say? That it is very easy to check directly that if g is a continuous function, then u is defined by the equation number 2 is indeed a function of equation number 1. From 2 we have u of x comma t is equals to g of x minus tb. We have discussed it before that u of x comma t is equals to g of x minus tb. Now what we do is differentiating this equation with respect to t. So ut is equals to g of x minus tb, we denote it by d of g x minus tb, and when we differentiating this with respect to t, we will get minus of b, because t differentiate, okay, 1 हो जाएगा, and ut is equals to minus b d, let x minus tb is equals to xi, so dg xi. Now differentiating this equation with respect to x du, here u with respect to t and here with respect to u, that means dg, here we take x minus tb is equals to xi, and when we differentiate x minus tb with respect to x, we will get 1, so dg xi. So put this ut is equals to this and dz is equal to this in the equation first, which we consider in the initial value problem, that ut plus bdu is equals to 0 in rn cross 0 to infinity. So what is the value of ut? Minus b dg xi plus b d xi. Cancel out, equals to 0. That means for t is equals to 0, u of x comma 0 is equals to gx in rn cross t0. This is the first condition when ut plus bd is equals to 0. Here we prove the first condition, and here For t is equals to 0, we take the plane Rn cross t is equals to 0 where u is equals to g. So here we also prove that u of x comma 0 is equals to g of x in Rn cross t is equals to 0. Hence the proof of the theorem of the initial value problem